and contemporary technology, bringing industry, academia, and experts, professionals together on the same platform by regularly organizing international conferences, national conventions, all India seminars, one-day seminars, conferences, workshops, roundtable conferences, and panel discussion almost throughout the year, having almost one program every fourth day. I'm glad to inform that the Telangana State Center is organizing 18 endowment lectures every year on the birthdays of the eminent engineers like Engineer V. Subbarao, Engineer M. Tirupati Reddy, Dr. J. Purushottam, Engineer Koka Krishnamohan Rao, Engineer J. V. Subbarao, Engineer T. Hanumantarao, Engineer A. P. Ranganatha Swami, Dr. S. Raghavachary, and Dr. Narla Tata Rao, and Engineer Matur Gopal Rao, Engineer Gurram Kodreddy, Engineer Akshari Venkateshwar Rao, and Dr. John A. Murray, Dr. N. V. R.L. Rao, and also Engineers L. Venkatakrishna Iyer, K. V. Srinivas Rao, and Engineer M. L. Swami, Dr. A. Ramakrishna, and Engineer I. Baswaraju, endowment lectures. I wish to inform the elite audience and take this opportunity to say a few words about the veteran and legendary engineer, Professor Dr. S. Raghavachary. Professor S. Raghavachary, born on 15th August 1939, obtained Bachelor of Engineering in Civil Engineering from Osmania University in the year 1959. As a topper, Professor Raghavachary served as a junior engineer with PWT Andhra Pradesh during the year 1959 and 60. During 61-63, he was technical teacher trainee at the University of Roorkee and obtained his master's degree in highway engineering. Thereafter, joined in 1963 as a lecturer at Osmania University, where he served the university till 1969. Prior to joining REC Warangal as the assistant professor and served REC till the year 1999 as professor of civil engineering. He obtained his doctoral degree in the field of transportation engineering in the year 1976 from the University of Roorkee. He was considered to be the authority in the field of traffic engineering and transportation planning in India. He led the comprehensive transport studies of Hyderabad urban development area in the year 82-86 from REC Warangal. Befitting to this, he had a rare distinctions and awards to his credit, and to name a few of them, Dr. T.S. Reddy will be taking over from me and will be explaining about the further of Dr. Raghavachary. And these usually all the endowments are being delivered by eminent professors with considerable professional experience to throw light on the important emerging topics of S. Raghavachary Endowment Lecture on Design and Evaluation of Concrete Pavements by Dr. K. Sudhakar Reddy, who is a professor of IIT Kharagpur. On behalf of the Telangana State Center of IEI and on my own behalf, Speaker Dr. K. Sudhakar Reddy Garu and all of you to this important event. And thanks to one and all. Now I request Dr. T.S. Reddy Garu, FIE, Scientist CRRI, and convener of this event to kindly brief about late Dr. S. Raghavachary Garu and also introduce the today's speaker. Over to Dr. T.S. Reddy Garu. Thank you, sir. Thank you very much.
Good evening to everyone. I, on behalf of our association, IEI Telangana Center, and on behalf of the students of Professor Raghavachary, I welcome all of you to this lecture. And it is a privilege to talk about Professor Raghavachary. Those of you, who have been either come in contact with Professor Raghavachary would have known him. And Mr. Brahmananda Reddy has already read out the biodata. He is born on 36, and then he graduated from Osman University. Apart from that, he was, probably it is the apt word to describe him is, he is Ajata Shatru. He is the one who never had any enemies or anybody who, there is hardly anybody who would have criticized him or talked about him in a negative manner. In the sense, he is a great personality by himself. And one thing I would like to tell about Professor Raghavachary is that he is I must call him as a genius on anything that, any subject, whether it is civil engineering or electronic engineering or mathematics, whatever it is. If he is given a book and ask him to teach about it, within 1 week, he would have mastered it and he would have claimed authority on the subject. That kind of person he was. And Professor Dr. Nagbhushan Rao is there in the meeting, and I also see Anand and Subhana have joined the meeting. Very, very glad to see all of you. And then, there are probably hundreds of students who have graduated. And all of them are in very good positions at different places. Professor Chary was a kind person, and he had contributed a great deal to the profession. Probably the traffic engineering, probably he was the first PhD in traffic engineering who got PhD from India. He went to Roorkee University all by himself. He first time, he did transport in PhD in transport engineering from Roorkee University, where hardly, there was any expert even to guide him. That is a kind of, he is very kind, and he had been a leading light for the students, and he had been guiding them, probably even throughout their careers. That is the kind of thing. And I have greatest regard. If we were in some position in the profession, it was because of Professor Chary. That is what I would like to say. And I also thank Professor Sudhakar Reddy Garu to have accepted to deliver the lecture on design and maintenance of pavements, rigid pavements particularly, which is very, very difficult. We see on road, wherever rigid pavements are there, rigid pavements are very good, if they are in good condition. If they start, giving problems, it's very difficult even to manage or repair. So I'm sure, all of us will get benefited by his lecture. And I have greatest regard. I pay my respect to Professor Raghavachary on this occasion. Thank you very much. And I have, may I request Professor Sudhakar Reddy to start his lecture, please.
Thank you, Professor T.S. Reddy. Thank you all the officiating members of Institution of Engineers Telangana, and my greetings to all the students of Professor Raghavachary. It is a great privilege for me to deliver a lecture, Professor Raghavachary Endowment lecture. Though I cannot claim that I have a long association with him, I met him several times, including PhD interview, rather a job interview that I attended for JNTU, long ago. He was the interview committee member. I did not get the job. Of course, that's a different issue. I didn't have PhD then. There were better candidates. And he was at Kharagpur as a PhD examiner. I think I met him at Professor Josso's retirement function. The last time I met him possibly was when I attended a workshop in Hyderabad, which he also graced that occasion. As Professor T.S. Reddy mentioned, I found to be very kind. He was very patronizing to me whenever we met, and very kind. And I'm sure he would be equally kind to all his students and then mentoring them. So once again, thank you very much for giving me the opportunity to deliver Professor Raghavachary Endowment lecture. I think I don't know whether you are functioning from the same office. I attended a lecture in this office a long time ago when I was working as an assistant executive engineer in CERP in the secretariat. Let me start my presentation. I will try to keep it brief. And you notice that my lecture is not exactly titled the way it was circulated, but the issues that I am trying to discuss are the same. So if you have any questions, I don't know whether it is a practice or not, I would be happy to answer your questions, anything related to concrete payments. So let me start sharing my screen. One of you may please let me know whether my voice is loud enough and then clear enough.
Your voice is okay, sir. You have to share the screen.
Yeah, I'm just sharing the screen. You can see my screen?
Yes, sir. Yes, sir. It is coming. Okay.
So in this, what I intend to do is I identified certain critical issues related to concrete payments. As Dr. T.S. Reddy just mentioned, when they function, concrete payments are wonderful. But we seem to be not knowing how to construct concrete payments, even how to design and then maintain concrete payments. We seem to be still learning as to how to do these things. So whatever was my experience, based on my experience, I identified few issues. So I would like to discuss those. After discussing some critical issues related to different types of concrete payments, I identified 3 different types of concrete payments. I will very briefly discuss about salient features of those in a common framework. So we all know concrete pavement is a pavement in which we have a concrete layer in different forms placed over different layers. The foundation layers, though typically we assume concrete layer plus the granular base or DLC, anything placed on subgrade is the pavement, and subgrade and below is the foundation. But when we start analyzing concrete pavements, concrete pavement being the predominant structural layer, many a time all those layers below the concrete layer, we consider them to be foundation layers. Hence, I listed dryline concrete base layer, cementitious base layers, various kinds of cement stabilized materials, including bituminous layers, including emulsion or foam treated base layers, unbound aggregate layers, and subgrade, stabilized, unstabilized, all kinds of layers which we place below the concrete layer as foundation layers. You can have various kinds of concrete pavements depending upon how we construct them. This is a continuously reinforced concrete pavement. I should actually prefer to call it as a continuous concrete pavement. There is reinforcement because we are trying to place concrete continuously without joints. So this is theoretically a continuous concrete pavement without joints, though it may have some joints, but by design, we don't need to provide them. Since there are no joints, for particular reason, we also provide longitudinal, sometimes transverse reinforcement also. So this is one category of continuously reinforced concrete pavement. This is a similar pavement where, for example, roller compacted concrete pavement, where we may not have joints by design. We can place the concrete continuously. Afterwards, you may or may not cut joints. This is our conventional concrete pavement, jointed plain concrete pavement, which we normally use on our national highways, 4.5 by 3.5 slab, transfer joint spacing at 4.5 meter, spacing. And then long tunnel joint, every lane is separated by a long tunnel joint. So typically a slab size is 4.5 by 3.5. You can have pavements with smaller slab sizes, smaller panel sizes. Obviously for that you need to cut the grooves at closer interval. This is the smallest size of concrete panel. This is also concrete pavement, you can consider that. If this is concrete and if these are blocks, you can consider this to be concrete pavement. This is another form of concrete pavement, which is promoted by my late teacher, Professor B.B. Pandey. These are plastic shells, and we're pouring concrete into that. I'm not interested in actually going into the details of what is self-fill concrete pavement. I'm only interested in discussing about how this is different from other types of concrete pavement. And in the framework of understanding concrete pavements, what are the issues that will be different in the case of self-fill concrete pavement? So these are plastic shells. We are pouring concrete into that. Okay, so we'll see what is different here. So you have different types of concrete pavements, starting from block pavements, precast, cast in situ block pavements, and typical conventional highway concrete pavement, smaller panels, and continuous concrete. You also have what is called as white topping, concrete over asphalt layer, bituminous layer, and among white topping, the concrete layer being thin, thick, different kinds of names that we use depending on the thickness of the concrete layer. And you can also have black topping over white topping, bituminous layer over concrete layer. We also the total thickness of concrete placed in 2 layers, wet on wet, and then maybe you can use inferior grade of concrete at the bottom layer, and upper layer could be functionally required layer and better quality aggregates. So in all this, what defines the kind of concrete pavement is the size of the panel and how we create it. For example, you consider this is a smallest size of concrete pavement in terms of panel size, which is precast blocks or precast panels. You can prepare them elsewhere and then bring them to the site and then place them and then construct a block layer. You can also do the same thing with a panel layer. So what happens is we also used to have a construction where we construct concrete pavement panel by panel. So there is no interlocking between these adjacent panels. If that were to be the case, for example, you've got 3 panels constructed independently, one after another. If you place a load here, then these 2 would not share the load. That same thing is depicted here. There is a middle panel. I'm placing a load here. These 2 panels would not be able to share the load because there is no load transfer mechanism between these 2. This is one kind of a concrete pavement. On the other hand, we create those joints by pouring concrete and then cutting grooves here. For example, this is a transverse groove that we cut up to 1/3 depth of the slab. And we expect a crack to form below the groove. So once you have a groove, this panel is separated from the adjacent plan. So a groove and the crack formation below that ensure that you have panel of size that you created, maybe 4.5 by 4.5, 4.5 by 3.5, whatever is the joint spacing that you consider, transverse and longitudinal. Okay. So this is a common form of joint creation that we do on national highways. But let us see the implication of this. And this is also a joint, a kind of concrete pavement that I just discussed, which is self-fill concrete pavement. So you got these plastic shells, we are pouring concrete into that. So this is what we expect. So the plastic wall is expected to bend when you pour concrete and roll it or vibrate it. So as it bends, these 2 adjacent blocks are interlocked because of the irregular shape. If you can see those blocks which are taken out from a self-fill concrete pavement, you can see the irregular nature of the vertical faces of these blocks. That creates interlocking between adjacent blocks. So this is a cast in situ interlocked concrete block. This is similar to your interlock concrete block pavements, but those are normally precast. This is a cast in situ. So if you place a load on any one of those blocks, you can expect that the blocks around that will share the load. But if this doesn't happen, you do not have a load transfer happening. Each block will be transferring the load to the underlying layer by itself. So the interlocking mechanism at the joints, the type of joints that we create is very critical in defining what is the size of the panel and over what area there is load transfer occurring. For example, if you do not provide any joints and pour concrete over a very wide area, say maybe 5 kilometers together, and then very wide pavement slab, what would happen is it would crack. Because as the slab tries to contract, because of reduction in temperature in winter, if it is restrained, there will be thermal stresses and it is going to crack. Most of you know all this stuff, but let me quickly go through that. So you do not know what is the spacing at which it is going to crack. You can roughly estimate that. It would never be able to, you will never be able to estimate it precisely. So there is going to be transverse cracking at some spacing, and there could also be long-term cracking if the slab is too wide. So too wide slabs, there are going to be long-term cracks, and very long slab, there are going to be multiple transverse cracks, as you can see here. So if you take an element and then increase its temperature, it is, let's say by delta T, if you know its elastic modulus value and then coefficient of thermal expansion, you know this is the thermal strain, and this is the multiplied by modulus value, that is the thermal stress. If you're trying to prevent the element from expanding, there is a compressive thermal stress, all of you know that. Similarly, if it is trying to contract, but we do not allow the member to contract, then there is going to be thermal tensile stress. For a simple element, you can calculate the thermal tensile stress as modulus value, coefficient of thermal expansion, into drop in temperature. What is drop in temperature? We'll discuss. So if this exceeds the tensile strength of the material, you can expect a crack, tensile crack. So if the expansion is restrained, you can expect compressive stress. If contraction is restrained, you can expect tensile stress. What restrains the contraction or expansion of the slab, we can discuss that. But what is more critical is, if I want to calculate what is the maximum thermal stress that is going to be produced in an element whose temperature is getting reduced, we need to know what is going to be the drop in temperature. You can always estimate what is going to be the coldest month of the year, what would be the average daily temperature, maybe you can estimate for a given site. But what is the initial temperature? It is very difficult to establish. Initial temperature is that temperature at which concrete gains strength after we placed it. During the design stage, most often, you would never know during which month the concrete is going to be placed. And when the concrete sets and gains strength, what would be the temperature of the concrete? Very difficult to establish, but there are some empirical guidelines that are available, which suggest that you can take average daily temperature during the month the pavement is expected to be constructed. If you can guess during which month the pavement is going to be constructed, you can approximately estimate what could be the initial temperature of the concrete. The final temperature is coldest month of the year, average temperature. This is the drop in temperature, which goes here, and you can calculate the thermal stress. So this would be the maximum thermal stress to which the concrete is going to be subjected to when it is trying to contract. The contraction is fully restrained because of some reason. What restrains the slab from contracting? Obviously, it is the foundation layer, the friction between the slab and the foundation, which restrains the concrete from contracting. So in this context, the coefficient of thermal expansion of aggregates that we use are very significant. Suppose, as you can see, it is E alpha delta T for a simple case. Quartz can have as high alpha value as 6.6. When compared to that, limestone can have as low as 3.8. This is very relevant. The kind of aggregates that we're using, their coefficient of thermal expansion will have an impact on the cracks at which the spacing at which the cracks would form if there are no joints created, or the spacing of the transfer joint that we need to create, that has to be significantly dependent on the type of aggregate that you want to use. For example, many agencies elsewhere, let's say in US and other countries, if they are using limestone aggregates, they recommend a spacing of almost about 6 meters. On the other hand, if these are quartz aggregates, the spacing would be as low as 4.5 meters. 4.5 is what we use in India, typically for transverse joint spacing. But if you are using limestone aggregates in your concrete, your spacing of transverse joints can be increased to as large as 6 meters. The restraint to concrete contraction is mainly produced by the interface between the concrete slab and the foundation, the friction that is mobilized between these two layers under different conditions. I'm producing some results produced by one of my former PhD students, who is a faculty colleague at IIT Kharagpur, Dr. Swati Maitra. She did some experiments on different types of concrete slabs placed on different types of foundations with and without a plastic sheet. We know most of our national highways, below the concrete slab, we put a plastic sheet. We also have the kind of construction where we eliminate the plastic sheet, place the concrete directly on dry-lean concrete. So these are the results that we get. When you place the concrete slab on wet mix macadam aggregate layer, this is the average value of friction that is mobilized, 0.35 to 0.77, when it is placed on a smooth interface with a plastic sheet. And without a plastic sheet, the range of values was in the range of 0.82 to 0.87. You can see the difference when you have a plastic sheet. Plastic sheet doesn't make it absolutely smooth. It would still have significant amount of friction, but compared to rough interface without plastic sheet, the friction is significantly reduced. Whereas when you place concrete over DLC with a plastic sheet, the range was 0.46 to 0.77. And over with a rough interface without a plastic sheet, we could not actually measure the screw jacks were not adequate to actually push the slab because the friction was as large as 20. Now there is a critical issue here. When you cut grooves and then expect that there is a joint that is formed and you created a panel of this size. This is called a joint activation. You cut a groove. Typically, this is cut to 1/4 to 1/3 depth of the slab. You weaken the slab there, and when it tries to contract or shrink, you expect a crack to form here. Right? For example, no crack forms here, no crack formed here, and maybe all these joints crack. We have maybe 4.5 meter long slab here, 4.5, 4.5. This is a 9 meter slab. So those of you who had the opportunity to examine failed concrete pavements, if you could notice whether there is a crack that has formed below these grooves, you would find in many cases there was no crack below the groove. That may be because the joint spacing that you consider 4.5 is too small, because you are putting a plastic sheet there. The aggregate that you are using may be of such quality whose coefficient of thermal expansion may be small. So the expected thermal stress, which would crack the slab at 4.5 meter spacing, is not getting mobilized. It can only crack the slab at 9 meter spacing. So if that were to be the case, what you are actually creating is a 9 meter long slab. Similarly, if the long tendon joint doesn't crack, you might actually create a 9 meter by even 7 meter slab, even wider slab, maybe 10 meter slab. So many a case what we're doing is many of these pavements, we're actually having panels of size which are much larger than what we thought we were creating. What we thought we created was 3.5 by 4.5 meter slab, but what we're actually creating, because there is no crack forming below the groove, which we call as activation is not happening. So we are creating larger slab sizes. So that will have an impact on where the cracks will form in the transverse and long direction, and what is the size of the slab that is undergoing curling. Many of you know what curling is. If the temperature differential, there is a difference in temperature between top and bottom, it would either curl this way or curl this way. This would be a typical daytime case. This would be a typical nighttime case. But full curling is not permitted because of the self weight. This will pull it down. Similarly, the self weight will pull it down. It would not remain completely flat. Some amount of curling will happen in the slab, but not complete curling. So since there is a restraint to curling, we are not allowing the full curling to happen because of the self weight or because it may be bonded to the layer below. How much resistance the foundation can offer to the lifting of the slab is a difficult thing to estimate. But let us assume, because of self-weight, the slab is trying to be brought back. Full curling is not allowed. So we assume that full curling is prevented, and we calculate what is the curling stress, the corresponding flexural temperature stress. So a similar phenomena is there when there is a moisture gradient. If you got hotter conditions here, you have smaller level of moisture. This would have more moisture. So the moisture gradient will be in the opposite direction to the top temperature gradient. So people can estimate, one can estimate what would be the stress produced by moisture gradient, the same way as you estimate the temperature curling stress. See whether the slabs actually curl or not. How much of the slab curling is actually restrained by the self-weight of the slab? We were making some experiments on National Highway 60. This is Kharagpur Palasur bypass road. We put dial gauges here. We have got a frame which was measuring the vertical profile of the slab. We were also trying to measure the temperatures of the slab at different depths so as to get the temperature profile, temperature gradient. And then simultaneously we were measuring the temperature profile and also the lifting up and down of the slab. We set up this experiment near a toll booth. And these are the variations of temperature profiles at different hours of the day, daytime as well as nighttime, positive and then negative temperature gradients. This is the movement of the curling of the slab movement up and down at different hours of the day. What is depicted is the daytime movement during different hours. There was one time at which the slab was almost flat and then it starts lifting up. This is an exaggerated figure. The slabs don't lift up by that much, but fact is that slabs would actually lift up and down during the course of the day. So curling happens. Okay. But part of this is restrained. This is what is happening after the total curling is restrained partly because of the self-weight and the connections with the adjacent slab and connection to the foundation. So when you compare large slab to small block, the block pavement to the continuous concrete pavement, these are the things that are going to be different. The panel size is going to be different. What would be the panel size is a function of how many joints are got activated. So do you have 4.5 by 3.5 or 9 meter by 7 meter slab? So that is a critical issue which will govern where the cracks would form, what will be the stresses that will be produced. And typically the thicknesses of large panels will be larger. As you reduce the size of this panel size, you can actually construct concrete pavements with smaller thicknesses. And another very critical thing is what is the load transfer mechanism from one panel to the adjacent panel? Because when you place load on a pavement, because that should distribute load over a much wider area, whether it is a block pavement or a large panel concrete pavement, we expect adjacent panel to share load. But we have seen in some kind of construction where you construct the concrete panel layer by panel, there is no load transfer mechanism. Whereas when you create interlocking mechanism, there is definitely load transfer mechanism. So creation of load transfer mechanism across these panels is very critical for the performance of these pavements. So this could be through some cases there may not be any load transfer because the blocks are no physical connection. There could be aggregate interlocking. We might put dowel bars connecting adjacent blocks or adjacent panels to transfer loads. And depending on the size of the panel, the critical load positions will be different. So what is relevant in the case of large panel, which would produce top-down cracking and bottom-up cracking, will be entirely different as you go on varying the panel size. If it is 2 meter panel, there would be different critical load positions. If it is 1 meter panel size, and different load positions are going to be critical. So which combination of critical load positions and temperature gradients need to be considered for large slab to small block? This is a critical issue. And what is the mechanism of load distribution by the concrete layer? Is it mostly by bending or mostly by direct compression? Obviously, the small blocks, there won't be much of bending. So flexural stresses will not be critical. Maybe compressive stresses, crushing stress would be more critical there. And in the case of large panels, flexural stress is going to be more critical. So when you consider large panel to small panel concrete pavements, or even continuous concrete pavements, this is the framework within which we are going to examine all these types of concrete pavements. What is the definition of performance? And what are important material characteristics that are relevant if it is a large panel concrete and if it is a small panel concrete or block pavement? Which property of concrete is more relevant? And what are the important loading considerations that we need to take into consideration? And what are climatic considerations? We'll quickly go through this. We all have studied about functional performance, structural performance, so I'll not go into those details, but we understand for any kind of concrete pavement or any pavement, functional performance is about comfort and then safety, and of course economy. So safety is about having a surface profile which has got adequate skid resistance, friction, so that vehicles can come to a safe stop. On the other hand, comfort is about how the surface profile varies over its length or over its length and width. Okay, so you can quantify that in terms of some roughness index, that is your comfort. So what contributes to roughness or what contributes to comfort, that we need to understand. And skid resistance is primarily an issue related to our construction practice and our metal selection. On the other hand, we need to maintain the concrete layer in an adequate structural condition so that it would not adversely affect the functional performance. We know in terms of roughness or comfort, rougher pavements are less comfortable, and then maybe smoother pavements are more comfortable. Smoothness is not about having very smooth planar surface. It is about less variation in the surface profile. So the variations in the surface profile produce vibrations in the vehicles, produce movements in the body of the passengers or drivers who sit in the vehicle, various kinds of vibrations. And there are certain critical vibrations, accelerations, velocities. One can correlate that to the comfort level and even injury of the people sitting inside the vehicle. So people have been able to correlate the surface profile to comfort level. And you got cracks, you got joints, problems, and if there is a plastic deformation and so on, they will also contribute to discomfort. This is about what causes comfort, discomfort. And we typically measure roughness or comfort using various kinds of equipment. Fifth wheel bump integrator, or in terms of international roughness index, or we use other equipment such as Merlin machine, or we express that in terms of what is called as present serviceability index. There are various ways of expressing the roughness which is related to the comfort. So every kind of a structure, every facility, you need to expect some performance from that. So you have to define what are we expecting from more roads. So unfortunately, the only performance indicator that we have documented in our documents in India is in terms of the roughness, measured using a fifth wheel bump integrator or by other similar equipment which express roughness of the road. The current guidelines that we have for concrete pavements given by IRC Special Publication 16/2019 are the roughness, which is called as unevenness index, as measured by fifth wheel bump integrator, should be less than 2000 millimeter per kilometer for good roads, 2000 to 2400 for fair roads, and more than 2400 for poor roads. For expressways, national highways, and then state highways category. For other categories of roads, you can see the numbers here, including village roads, good road less than 2200, and then fair road 2200 to 2600, poor road 2600 millimeter per kilometer. But when we design, it would be very difficult for us to control the kind of roughness that we expect during its service life period. There is hardly any design parameter which we can vary or control so that the roughness can be controlled. What we can control is to ensure that it doesn't crack, it doesn't undergo plastic deformation, the foundation is not eroded. These are things that we can control through design process, increase the thickness, make the foundation stiffer, maybe control the size of the slab. These are our design variables. So thereby we can control the stresses, deflections, in the layers of the pavement. But can we control the roughness of the road surface, how the profile is going to vary directly through our design process? Very difficult. But our guidelines for performance indication in India are currently in terms of the roughness or unevenness index value. Compared to this, if you look at the mechanistic empirical pavement design guide for jointed pavements as well as continuously reinforced concrete pavement, let us look at jointed pavement because this is what we normally build in India. There is a joint folding, which is a problem with concrete pavements. At the joint, both the slabs are at different elevation. So the average joint spacing should not be greater than this. For interstate highways, there is a criteria for that. The load transfer efficiency, theoretically there is no criteria, but we expect a certain level of load transfer efficiency. Let me skip this. The amount of transverse cracking, the percentage of slabs having certain degree of transverse cracking should not be in excess of 10%. This is a performance indication in terms of physical problems that you see there. There is a performance indicator in terms of joint spalling. There is also an indicator in terms of roughness. If you can estimate all these, they go as an input parameter for estimation of roughness. So you can control the roughness directly in terms of these parameters. Similarly, if it is a continuously reinforced concrete, you have got similar parameters. What I'm trying to say is the mechanistic empirical pavement design guide, MEPDG, talks in terms of cracks, talks in terms of foundation erosion, talks in terms of the spalling that occurs near the joints, the joint falling that occurs near the joint. It talks in terms of those physical problems which you can see and measure and quantify, and it sets limits on those. But India, the current guidelines are only in terms of roughness. They also have criteria in terms of roughness, but they have criteria for more important distresses, structural distresses, which you can control in our design process. These are typical problems that we have with concrete pavements, various kinds of cracks, narrow cracks, large cracks, and depending on the position, corner cracks, mid-slab cracks, and so on, full length cracks, full depth cracks, wide cracks, and so on. You can see these are cracks where there is faulting also there. Both slabs are at different elevation. So there are various types of cracks that form because of various reasons. And once you have cracks, you have other disintegration of the slab that is occurring near the corners locations and mostly near the joint locations. And edges of cracks, you have the slab disintegration happen. This is a failure that I have not seen in India previously, but someone shared some photographs with me. This is not an Indian failure, but blow up is a failure that happened in India also. This is when the slabs try to expand. There is not adequate gap between these two slabs to accommodate the expansion. You can expect a blow up happening like this. This is the failure of foundation. The foundation layers are getting eroded and coming through these cracks and joints getting deposited. So since there's a mud that is getting deposited, we call it also as mud pumping. But basically, this is the loss of support, especially if you got fine material there in the foundation. And if it is wet, you are subjecting those slabs to application of heavy loads, and there is a pumping action. So you can expect pumping of fines happening from the foundation layers. Now, when you characterize the concrete material for various purposes, when you're trying to explain different kinds of pavements, there could be crushing, small blocks. There is not contraction cracking because it is too small a slab. To be worried about contraction cracking because there is hardly any restraint, and then slab is too small. Right. But they could be subjected to crushing. So crushing is an issue. Direct tension, when you got large panels and you cut a groove there, whether it's going to crack or not, is because when it is trying to contract. So this would be a case which is more relevant for direct tension instead of flexure or crushing. But you know, when you place load on a slab, it is going to bend, or when there is a temperature gradient, it tends to bend. So flexure is an issue. So we know that there is a modulus of rupture is a relevant property to find out flexural strength and compare that with the stress that we apply. But we also know that even smaller loads produce failure because of the phenomena called as fatigue. When P is less than P failure also, when you apply it repeatedly, it can cause failure in the pavement. So the fatigue characteristics, flexural strength, direct tensile strength, and then compressive strength would be the relevant properties when you start explaining small block pavements to large block pavements or large panel pavements. When you consider climatic conditions, these are different issues: variation in temperature, temperature gradients, and then the maximum temperature, minimum temperature to which the layer is going to be subjected to, the temperatures when the slab initially is set and then gains strength. Was there any temperature gradient when the initial setting happened? So these are the issues that we need to consider in our design. We have various kinds of loading that is, the concrete pavement is subject to different kinds of vehicles as defined by IS 3, 1983. Various kinds of axles, tridem axles, single axle, dual wheel, single wheel, all axle configuration are there. These are different axle configurations for which these are the legal loads that are prescribed by Ministry of Road Transport Circular. Single axle, single wheel, single axle, 2 wheels, tridem axle, 12 wheels, and so on. This is the maximum permissible limit. What I'm more interested in rather than the legally permissible load limit is the axle configuration. This is the wheel load configuration for a single axle, single wheel on either end, and then single axle with dual wheel at either end, tandem, tridem with 2 wheels on each axle. These are tandem tridem with single wheel at either end. You might have seen axles of this configuration also. So when you consider different panel sizes, and then should we put one axle to should we put 2 axles, only one set of dual wheel is going to be critical. This is what I was discussing when the slab size varies from a very large panel to small panel block. So the number of wheels that you can accommodate there and the kind of failure that it would produce, transverse cracking, long-term cracking, top-down cracking, bottom-up cracking. So the load positions are going to be critical. But as we know that this is a typical conventional concrete pavement that we adopt for national highways, your thick concrete pavement, there's a groove that is cut, there's a crack that has formed below, plastic sheet, dry laid concrete layer, granule layer below that, and the foundation layer. So as per Indian Roads Congress guidelines, I'm quickly going to discuss 3 different kinds of pavements. The conventional jointed concrete pavement as per IRC 58, I'll summarize the design features. I'll not go into too many details. We know that we typically go for 4.5 meter transfer joint spacing, and every lane we try to separate with a long tunnel joint. So 3.5 meter long tunnel spacing, 4.5 meter transfer joint spacing. So typically we are creating 4.5 by 3.5 meter panel sizes, assuming there is activation of the joint at every groove that you cut. And we have got drilling concrete plus granular layers as the foundation layers placed over prepared separate. And we check the slab for cracks that initiate from the bottom, cracks that initiate from the top-down cracks, bottom-up cracks. In the transverse direction, typically long-term direction, the occurrence possibility of that is less severe than the transverse cracking. And the combination of loads that can produce bottom-up cracking and the positive temperature differential, similar to the combination of loads and the temperature differential that produce top-down cracking have been identified in IRC 58. The number of loads that can be combined with maximum positive temperature differential, the number of loads that we can combine with the maximum negative temperature differential have also been identified. And we calculate what is the total cumulative fatigue damage caused by all those affected loads during the design period of 25-30 years. And then accordingly assume that if the total damage doesn't exceed 100% or 1, we assume that the slab is going to be okay. So this is our performance criteria, that the estimated, theoretically calculated cumulative fatigue damage should not exceed 1 or 100%, but we do not know what it actually physically means when it is translated in terms of number of slabs that crack, number of slabs that have got joint faulting or other kinds of problems. So we do not have a physical visualization of what is performance when we design a pavement for 30 years, what you can expect in terms of those physical problems. We're only theoretically estimating the total cumulative fatigue damage and then ensuring that that is less than 1. So these are the two types of problems that we consider. Daytime, when the slab is trying to curve like this, and when you place a load like this, it can produce a bottom-up crack, which will progress upwards, which is called as a bottom-up cracking, and find out how many loads are relevant for producing this kind of a failure. During daytime, how many axles would be there, which can be placed in the middle of the slab, and then count them, and then find out the cumulative damage caused by all that number. So typically, if it is a transverse cracking case, single axle you place in the middle, tandem axle, this would be the load position. You subject this to positive temperature gradient so that it will have the tendency of curling as shown here. And then the combined action of load plus temperature differential would produce bottom crack. Similarly, during night time, there would be certain category of vehicles which would have the spacing between the front axle. The distance between them would be just less than the length of the slab, which is the transfer joint spacing. So you count those number of vehicles, and those would be in combination with negative temperature gradient, during which the slab will have this tendency. So this would produce top-down crack here. So count all those numbers plus the negative temperature gradient, calculate the fatigue damage caused by all those vehicles whose spacing between successive vehicles is less than transfer joint spacing, and then estimate the cumulative damage. That is relevant for top-down cracking. So these are the salient features. The analysis is carried out using finite element analysis. Foundation is considered as Winkler foundation, bed of springs, and there are concept called as zero stress temperature gradient, load transfer from one slab to another slab, load transfer from main slab to a paved shoulder. These are the salient features of jointed concrete pavement as per IRC 58. I'll quickly introduce a new type of concrete pavement. I think I'll just take another 10 minutes for this talk. Okay. As I already shown you, this is a continuous concrete pavement where we place concrete continuously. We may have some joint somewhere. If it is a construction joint, of course, you need to have a joint there. Sometimes we may have an isolation joint or expansion joint. But let us assume theoretically we place concrete continuously. As a result, we may have cracks forming there, and you may place reinforcement like this in the long-term direction. So these are the cracks in the side view that you see at irregular spacing, but more or less at regular spacing you can see them. Sometimes they could be random also. Okay. So you have cracks, and there is a reinforcement running through this. Hence, it is a continuously reinforced concrete pavement. So how are these different from your jointed concrete pavement? You should assume that this is your panel, which is created. This is separated from the adjacent panel like this because there is a full depth crack. Okay. So when you place a load on this, this should transfer load to the adjacent slab. That is the meaning of a layer. Otherwise, each block is working independently. So there has to be some load transfer mechanism across this. As you can see, these cracks are irregular in shape. So there is an interlocking that is happening between these two. So the function of reinforcement is to ensure that the cracks do not open up. The interlocking is maintained. So the reinforcement is designed in such a way that the crack spacing is controlled, crack opening is controlled, cracks do not open up too wide during winter. So that is the purpose of reinforcement here. Yeah, same thing is explained. This is the plan view. This is side view. In the plan view, if you do not have any joints, you can expect cracks to be forming at some regular irregular intervals. If the slab is too wide, you can also expect long-term cracks to be forming. So these would, if these cracks are full width, this is one panel, this is another panel, you can consider this to be a different panel. So the load transfer from one panel to another one, as I just explained, will happen through this interlocking. This slab is interlocked with the adjacent slab through this interlocking mechanism. We do not want this to be opening up too wide. Otherwise, the interlocking mechanism will get reduced. Load transfer to the adjacent slab is going to be reduced. The purpose of reinforcement, as I just mentioned, is to keep these slabs, the cracks tight together. Don't allow them to, they will not allow them to open up too wide, and maintain the interlocking adequately throughout the service life period. So the principle of this continuously reinforced concrete is going to be, we know that there is going to be cracking. So it is based on so let it crack, right? So people should accept that this is a pavement which is going to have cracks. When you cut grooves, they're in a regular fashion, so people will accept that. But this surface will have irregular cracks, so one has to accept that. Right? And we provide continuous reinforcement, as I already mentioned, to ensure that adequate load transfer is continuously maintained. The cracks do not open. So what is the design philosophy here? We have reinforcement here, you got slab there, and you are going to expect cracks to be forming, and they may be of different width, different spacing. So what we design these slabs are to ensure that they have got the slab spacing is controlled and slab width is controlled. The the joint space, the crack spacing is controlled, and the crack opening is controlled. We don't want it to be opening up too large. We don't want the crack spacing to be too small or too large. Both cases you will have a problem. Okay, I'll show what it is. This is the typical type of failure that would happen in the case of a continuously reinforced concrete pavement, because these transverse cracks, if they are too close to each other, and the maximum tensile stress would generally be produced at a location which is about 1.5 to 1.8 meters from the edge of the slab. So this piece breaks out, which is called as punch out. So when you talk about continuously reinforced concrete pavement, punch outs, how many punch outs you see per mile per kilometer is the failure criteria. So we're going to control these kinds of failure because we are going to have like narrow slabs, and when you place loads on this piece is going to break out, which is called as punch out. We're trying to control the number of punch out failures in a continuously reinforced concrete pavement. So our selection of reinforcement, thickness, grade of concrete, foundation, all this is to control how many punch outs are going to be there and how much spalling and so on. So there are three major design processes that are available. American Association of State Highway Transport Official, 1993 design guideline, and more recent mechanistic empirical pavement design guideline. We have one Indian Roads Congress 101, 1988, continuously reinforced concrete pavement with elastic joints. So these are typical design criteria that are adopted either in MEPDG or ASTO 1993. These are that the maximum allowable design crack width, the crack should not open beyond 0.5 millimeter. So your design should be done in such a way that the crack width should never be greater than 0.5 millimeter. Very difficult to control, but they try and then provide some design equations and analysis for that. So that there is no spalling that is happening. You don't want any hard metal to go into these cracks and then break the edges of the joints. You don't want water to be penetrating through these cracks. So keep the joint opening to a maximum of 0.5 millimeter. And the desirable crack spacing should not be smaller than 1.1 meter. And that is 3.5 to 8 feet. If it is smaller than this, your punch out problem is going to be more because you got very narrow slab and there is more potential for punch out cracking. If it is too large, very long slabs will contract more. The crack is going to be opening more. So you have more problem of joint spalling, breaking of the crack edges is going to be more if you got long slabs. So you don't want your crack spacing to be greater than 8 feet. You don't want the crack spacing to be smaller than 3.5. There is a way of controlling that during the design process. Typically, the long-term reinforcement is of the order of 0.6 to 0.7%, and the position of the long-term steel is placed at 1/3 to half the depth of the pavement. These are the expressions that mechanistic empirical pavement design guideline uses to estimate how many punch outs will be there per mile in terms of cumulative fatigue damage estimation, which is similar to what we do in Indian Roads Congress guidelines ISC 58. You find out how many load repetitions, temperature gradients, calculate stresses, calculate cumulative fatigue damage during the design life period, and accordingly how the punch outs are going to increase, empirically correlated, physically observed punch outs, and then theoretical estimated damage index, basically cumulative fatigue damage. They have developed correlations comparing the physical punch out numbers observed to the theoretically calculated damage index. This is what we do in IRC also for estimating what is going to be the fatigue life, so that we can estimate the damage index as a function of what is the stress produced by a given load, what is the flexural strength, which is called as the stress ratio, this is what we do in IRC 58 also. They're trying to convince us that their estimated punch outs and then measured punch outs match reasonably. This is an estimation of what is going to be average crack spacing for a continuously reinforced concrete pavement with a given thickness, given grade of concrete, and given reinforcement. Right? You can estimate that if you got all these inputs available. You can also estimate the crack width. Again, if you got all the inputs available, including temperature drop, coefficient of thermal expansion, and so on. These are the parameters that we're trying to control: crack width, crack spacing. And once you have all that information, in terms of damage index, in terms of punch outs, in terms of other problems related to the cracks, you can put them in your IR equation, which is your roughness or comfort. This is a comparison of predicted IRA with the measured IRA. The Astro 1993 have got nice nomographs available, which is nothing but solving this equation. This is for crack spacing. I will not go into the details of what are those variables. Obvious variables in terms of thickness, in terms of coefficient of thermal expansion, the reinforcement details, the concrete strength details. Okay. Similarly, you can estimate crack width. You can estimate the steel stress so that the steel doesn't get ruptured. I'll just take another 5 minutes to share some details related to short panel concrete pavement. Afterwards, if you have any questions related to any part of this, you can ask me those. This was a research scheme that was carrying out for National Highway Authority of India. And this is a PPT that was prepared by my PhD student. Suppose you want to reduce the thickness of the concrete slab, large panels will be subjected to more flexural stresses, more curling stresses. So you'll not be able to reduce the thickness significantly. Typically, we used to have thicknesses of the order of 330 millimeter, to 270 millimeter, 250 millimeter, right? So, but if you can reduce the size of the panel in terms of to 1 meter by 1 meter, 1.5 by 1.5 meter, so you are reducing flexural stresses, and then maybe you are actually converting to more of direct compressive stresses on the foundation layers. So it would be possible for you to reduce the thickness of the slab. So large panels distribute the load over much wider area, but mostly by bending a flexure. But as you reduce the slab, it would be less of flexure, more of direct load transfer. This is a Bangalore nice road, panel concrete pavement, short panel. This is basically the same way that you construct a normal concrete pavement, but you cut the grooves both in the long trend as well as transverse direction at much closer spacing. And if the cracks develop below these grooves that you cut, that means activated, then you got panel of this size. Provided the joints activate, that means there is a crack that is going to form below every groove that you cut. So this is the individual panel size, and they are interlocked between with the adjacent blocks. If you place a load somewhere here, maybe all these blocks will share the load because of the interlocking among those blocks. So typical panel sizes would be 1 meter by 1 meter to 2.5 meter by 2.5 meter. As already mentioned, smaller magnitude of bending stresses, smaller curling stresses. Right? The main issue here is you got more joints to be constructed and you have to maintain them. But since the joint width is smaller, the roughness or comfort level is expected to be better compared to more conventional concrete pavement, where the joints are going to open up much wider. I'm sharing a few details about a test section that we constructed on a National Highway for National Highway research project. These are different combinations, different panel sizes, different base thickness layers. Base was dryland concrete. We also constructed this panel concrete on dense macadam layer, which is typical white topping construction. And these are the thicknesses of different sections. The construction is constructed the normal way. Only difference is that you have to cut the grooves at closer spacing. So you have to plan for that because you got a specific time that is available for groove cutting, and you have to cure them properly. We're also trying to see whether sealing this is required or not required. We didn't find any effectiveness of sealing the cracks because the slab being small, they don't open up wide enough. So the sealing is not that effective here. This is a national highway that we constructed and inspected in 2017. So this is almost a 5-year-old concrete pavement on a national highway. We have carried out various kinds of structural evaluation of these pavements to understand what kind of load transfer takes place from one panel to another panel, and what is the level of load transfer efficiency, and what is the critical load positions for different panel sizes. For example, as you can see, if you got a 2 meter by 2 meter panel size, if you got a dual tandem axle, the front axle placed close to this edge, rear axle placed close to the edge, could be a critical load combination for producing transverse joint in this direction. Similarly, as the panel size varies from 1 meter by 1 meter to 2 meter by 2 meter, so there could be several combinations of load position. Just the dual wheel itself could be a problem. Tandem axles could be a critical position. So we identified several critical positions which can produce long-term cracking as well as transverse cracking. We have been measuring the degree of load transfer that can be produced. It is typically high, of the order of 85 to 90%. But when we produce design charts, we typically assumed it to be of the order of, let me show you that. Okay. This is how these panel concrete, whichever have failed, corner cracks and then long-term cracks. But most of the failures have happened because of the foundation failures. Let me show you this. For example, this row of panels failed. Once one panel failed, the adjacent panel started failing. This was because of the foundation that we had here. There was water accumulation. There was erosion of dryland concrete to foundation. Though dryland concrete is supposed to be non-erodible foundation, but you know, when there is water accumulation, continuous pumping of these panels by heavy loads, there is going to be erosion of all kinds of foundation. So this is one major type of failure that we observed. We didn't see this on white topping failure pavements, where we place the panel concrete on dense bituminous macadam layer. So this was the analysis of a panel concrete pavement, where we consider different sizes, different load positions, positive temperature gradient, negative temperature gradient, almost 30-40 different combinations of critical load position as well as temperature gradient were examined, both for long-term cracking, transverse cracking, top-down as well as bottom-up. We also carried out lateral distribution, lateral wander of wheel loads to identify for different critical combinations what could be the percentage of vehicles that we should consider. This is the results that we obtained from that. And this is the summary of recommendation for different load positions, different panel sizes, what could be the percentage of loads that we can consider for different critical failure cases, transverse cracking, long-term cracking, top-down, bottom-up. Finite element analysis was carried out, multi-slab, 9-slab system was used, and then slab placed on linear springs, slab placed on multi-layer elastic layer system also was done. Various panel sizes were analyzed. For conservative design, a load transfer efficiency of 50% was taken. We're trying to produce design charts and then stress analysis charts for varying load transfer efficiency. Typically, we will get much greater load transfer efficiency across one panel to another one. It would be of the order of 70-80 throughout the service life period. But assuming that there is going to be disintegration of these joints and the load transfer efficiency gets reduced, there will be more load transfer to the bending stresses as well as more stresses on the foundation. These are typical combinations that we consider. We have produced a lot of stress charts similar to the stress charts that IRC 58 used to have. These are produced in terms of regression equations. I think almost around 150 cases of critical cases are there. So 150 regression equations have been produced. This is the design methodology for panel concrete pavement. There is no design analysis procedure that is currently available for analysis of panel concrete pavement. We are currently using the analysis that is available for white topping, ultra thin white topping. So we believe that these are going to be useful for design of panel concrete pavements for high volume roads. I think that is about the panel concrete pavement. I don't know whether I was able to summarize the entire thing that I wanted to discuss about, but I would be happy if you can ask me some questions related to any aspect, whether it is design or evaluation or whichever concrete pavement it is. Thank you.
Thank you, sir, for your wonderful lecture and to great tribute to the Raghavachary garu. Anybody wants to ask any questions, please?
Anything related to concrete pavement?
May I ask any questions, sir?
Yeah, please.
Yes, sir.
Excellent presentation, sir. So very enlightening presentation. One thing is, what is the ideal time for cutting the groove for a concrete pavement? The second one is for municipal roads. Cement concrete roads. What is the panel size you recommend for ultra thin concrete roads? Ultra thin concrete pavement like that.
The second question first. So the smaller the panel size, the thinner could be the slab thickness. But of course, you need to maintain the panels, the joints. So it is very important for you to have a good foundation, because if your foundation starts eroding, you will have more serious problems with panel concrete. The kind of failure that I showed on National Highway, once the first panel failed, the adjacent panels started failing quickly. So you have to intervene immediately and then repair that panel. Otherwise, the adjacent panels will go very fast. So that is the main issue. So very large panel size, they're stable by themselves. They would not disturb the adjacent panels for quite some time. But the small panels, you need to address them immediately. So it is a question of how strong a foundation that you can create, and whether it is subjected to be moisture intrusion, because when you have moisture intrusion, of course, city streets, you should not typically have very heavy loads which would cause pumping action, erosion, unless you got a road where you allow trucks and other buses and other heavy vehicles, especially trucks. You need to be concerned about this pumping action, right? So then you need to have slightly larger panel size if you got that problem. Otherwise, smaller the panel size, thinner you could construct this slab. Your first question was related to, typically it is 8 to 16 hours. Okay? So, but that would vary depending on the actual conditions and the grade of concrete.
8 to 16 hours after laying of the concrete.
Yes.
For example, for the ultra thin concrete pavements, do you recommend these dowel bars?
No. Even our 2.5 by 2.5 meter panel size, there are no dowel bars.
Okay.
They're not required. The aggregate interlocking will is sufficient, more than sufficient for load transfer.
Okay.
The load will be shared over much significantly wide area.
Okay. Thank you. Thank you.
Sir, I have one doubt, not a question, because I am
Yes.
not a civil engineer, but from electronics.
Yes, sir.
You are laying down the pavements and whatever is concrete. Whether the soil has got anything to do with your size of the panel, what you are talking about it. If soil is not having strength, whether what is the size, whether it is a standard size used everywhere or depending upon the testing of the soil procedure. It's my doubt.
There are two. You have a second question, sir? That is a question.
No, only one question. That is
Okay.
whether
to the
soil
foundation
decides.
material, yes.
Yeah.
Yeah, when you actually call soil, typically our foundation consists of soil plus an aggregate layer plus a relatively stronger layer, which is a bituminous layer or cemented layer or even lean concrete, over which your concrete panel is coming, typically. But theoretically, you can place your concrete on your soil also directly, because that's a foundation, there's a concrete slab. So when you got varying soils or varying foundations with widely varying, let's say, strength values, there are two issues here. One is What is the friction that is mobilized? When you talk about panel size, the friction that is mobilized between the foundation and the slab is a critical factor in deciding what could be the panel size. Number two, when you got very poor soil, obviously the bending is going to be more, flexural stresses are going to be more. But for reasonable thickness, starting from, let's say, 250 to 300 millimeters thick slabs, the foundation contribution is not that great. Theoretically, otherwise also. So the foundation doesn't contribute significantly to the overall structural performance of the pavement in concrete pavements compared to its contribution in a bituminous pavements or flexural pavement. There are no guidelines devised in terms of what could be the panel size based on the foundation strength. But when you go for smaller panel, you need to have reasonably strong foundation.
Thank you, sir. Thank you. Anybody else, please? Any questions?
Do you recommend cutting of the groove? Cutting of the groove is required only for the pavement concrete, pavement quality concrete,
Yes,
isn't it? For DLC, it is not at all required, is it?
You can also do for DLCs, because sometimes when you actually do, it's a too good a DLC. So you are going to have cracks which are too wide. They can actually reflect into the concrete. So there are actually agencies or maybe organizations to recommend you cut also grooves in DLC also, and match your concrete slab joints with those of DLC grooves. That would prevent the random cracks which generate in DLC from propagating to the concrete slab. But it is definitely more difficult to do that. So we're not doing that currently because we are putting a plastic sheet most of the time.
Yeah.
I'll come back. Mr. Nitin Chari, please raise your hand. Anything you want to ask?
Sir.
Yeah.
Hello, sir. Yes, sir. Good evening, sir.
Good evening.
Sir, I have two doubts, sir. Like we will be providing the texturing to ensure the safety.
Yes.
So what is the ideal time for the texturing? And one more thing is, like over a period of time, the texturing will smoothen. And how the retexturing is done?
Yeah, ideal time is immediately after the place concrete. Either grooming or other techniques are available to provide the tining.
Yes, sir.
My small depth grooves are created.
Yes, sir.
So immediately after placing the concrete, the paver itself can do that. Okay. Otherwise,
Okay.
you can groom that. And then whenever you find the skid resistance reduced to levels that are not acceptable, there are various techniques using which you can cut grooves. There are diamond cutters that are currently used to create the grooves again on the pavement surface. Though may not be as effective, and then the same kind of grooves that you can produce initially, but the diamond cutting grooves are being created whenever you find the skid resistance below a given level.
Okay, sir. One more doubt, like we'll be placing the dowel bars. So one side will be fixed and another side will be free.
Right.
So like how we will place the dowel bar, like the free side will be in the direction of traffic or it's opposite to the direction of traffic?
Okay, I always get confused, so you caught me there. Okay. See, there are two issues here. Suppose the free end of the dowel bar is to ensure that it should not lock the joint, whichever way you do it. That is the principle of that. Okay. So when the slabs try to expand or contract, the locking of the dowel with the concrete panel should not create cracks there. So when there is actually deflection, suppose you place a load on one side of the dowel on one panel, when it is deflecting, so the deflected panel, you can actually do it both ways, right? So there won't be any significant difference whichever way you put the plastic cap on, rather plastic cover. Okay, but to me it should be on the following side.
Okay, sir. And one more thing, like we will be providing the tie bars or the longitudinal joints if our width of the pavement is greater than 4.5.
Yes.
And if my pavement width, which I am paving, is only 5 meters, even then also we need to provide the longitudinal joints or not?
Theoretically, you're supposed to provide. Otherwise, our assumption is that for the condition that we assume, coefficient of thermal expansion, friction that is mobilized and all that, we are assuming that 4.5 meter crack may be there. That is the maximum size of the channel. If it is larger than that, it may have a mid slab cracks. Most of the time it will not happen because you got a plastic shape.
Yes,
right?
sir.
So, but theoretically, if it is more 5 or more, you are expected to create a joint there.
Okay. Sir, and one more
But
thing.
5, you can still take a risk, because
Okay.
if you are putting a plastic sheet, you can take a risk.
Okay, sir. And even when we are paving the concrete pavement, say for example, if we are paving a paving quality concrete, usually we will prefer M40 grade, whose flexure strength should be greater than 4.5 MPa.
Right.
So can we go with the M30 grade by adding fibers in that, and we will enhance the strength and give that minimum required strength? Is it possible to provide that?
No, if you're saying a fiber added reinforced and then you're enhancing the strength, there is a flexural strength. That is the main issue,
Sir.
because you're comparing your flexural stress to the flexural strength. So if
Yes,
you can
sir.
produce M40 grade flexural strength by any means, that is fine.
Okay, so if we modify the mix and we will add some fibers to enhance that flexure strength and
Definitely,
take it around
definitely.
5.
I'm sure you'll be able to improve the fatty characters also.
Yes, sir. Yes, sir. So we may provide that.
Yes, sure.
Okay, sir. Thank you. Thank you for this
Hello?
informative session, sir. It was nice.
Hello?
Yeah,
Hello, sir.
Professor
Yeah.
Yes, please.
Vinayak Ram,
Hello?
Professor Vinayak Ram, kindly sir, is the
Hello?
question.
Sir, good evening,
Good evening,
sir.
sir.
Good evening, sir. That was a beautiful lecture, sir. I was really enjoying the whole lecture. My question was, for example, if you nowadays in the cement market, a lot of cements are coming, like different varieties of cements which are capable of producing high strengths with low thermal cracking possibilities. Like even the heat of hydration is very low, and very good cements are coming. So like with different GGBs and fly ash to be in combinations.
Right.
So in such cases, the kind of stress development is going to be different. Like we have been talking about in the IRC 58 code of practice or similar other code of practices, the stress development, like the joint spacing, the transverse joint spacing as well as longitudinal joint spacing, they're all decided based upon certain criteria. So did we have any research which has been carried out with the different grades of cements which are coming into the market right now? And what exactly is happening? This is my first question, sir. Regarding the second question, I was asking the precast blocks, like when you're talking about the national highway is being built with thin sections of cement concrete with 1 by 1 or 2 by 2 meters of blocks, which have been cut in the field in situ. So instead of that, if I go for precast blocks, what kind of performance difference is going to happen, and how exactly it is going to be different from different than the in situ kind of construction? These are the two questions which I have got, sir.
Thank you. I think your first question is related to, suppose if you use different grades of concrete, what could be its impact on the joint spacing? Is that correct?
Different grades of cements.
Yeah, different grades of cement accordingly,
Cements.
different grades. Yeah, sorry.
Yes, sir.
So
Yes, sir.
it's what could be the possible impact on the joint spacing that we need to adopt?
Yes, sir. Yes, sir.
Yeah, I think it's I don't think it would have a major effect on the coefficient of the rim expansion, but it might have greater tensile strength, and that could be the main governing factor. So if you can improve the tensile strength,
the amount of shrinkage stresses may be different, no, sir. Like
yes.
with different heat of hydrations.
Yeah.
Definitely the shrinkage, the way the shrinkage is going to happen is going to be different. So when we are using different grades of cements, what is the effect of that? And IRC speaks about maybe a very common case of using 43 grade of cement or 53 grade of cement. But right now in the market, we have got at least 20 varieties of grades of cements. So when we are using different grades of cements, what exactly is going to happen? So shrinkage, the kind of shrinkage which is going to happen is completely different, and obviously the shrinkage related stresses also are going to be different than what was assumed basically. So with regard to this, what exactly is going to happen is my question, sir, basically.
Yeah, I think what you pointed out is very relevant in the sense it is going to impact the shrinkage characteristics that as a result the joint spacing that we need to adopt. But I'm not aware of any study which has been carried out on shrinkage characteristics of different grades of concrete and linked that to the joint spacing that we can adopt. I have not seen that. Possibly it has been done. So I'm not yet sure. And then even that 4.5 meter thing, I don't think we have established and then finally settled that it has to be 4.5. Even the conditions which we assume for selecting 4.5, we're not documented that.
Yes, sir. Yes, sir.
Your
I
second part was
anyway,
that,
sir.
Professor, your second question was?
Yeah, that was regarding the precast option as well as
Yes,
the
yes.
in-situ option.
Yeah, no,
Yes,
there is a there are a couple of agencies in India which are trying to bring in this precast concrete construction, which is a patented one elsewhere. So they're actually trying to do some trial stretches. But very critical for that is to ensure that they are placed on a perfectly level foundation. That is the most critical thing. But that would be very convenient if it can be proven to be successful in terms of implementation. Theoretically, that is fine. I am personally aware that there is at least one agency in Maharashtra which is trying to do some trial stretches in collaboration with those foreign agencies.
thank you, sir. Thanks a lot.
Sir, Kumar sir, I'll just actually the TS Reddy is waiting. After that, he comes. TS Reddy, I think you're having some questions, sir.
Thank you, Brahmananda Diyaru. Professor Reddy, thank you very much for giving the lecture. It's a wonderful exposition on concrete pavements. I was just wondering, particularly in smaller towns and even villages, concrete pavements are being laid, left and right, and they fail probably within 1 or 2 years. Is there a way that we can rehabilitate them and salvage what damage has been done and then see, proper pavements or roads are provided in such situations?
Yeah,
have we made any efforts in that direction?
We can do that, sir. We have actually done work on rehabilitation and structural evaluation of in-service pavements, including low volume roads as well as high volume roads. Concrete pavements are very important. I think very important in the sense that I believe that they are the better alternatives to compare to all the other flexible because they're all moisture susceptible. Moisture damage is going to be very severe. So there are various options available, including complete rehabilitation, recycling of the material, providing overlays on existing concrete pavements. So several options are available. Most of our national highways also, there are now time for most of them to be rehabilitated, overlaid. We are only repairing slab one by one and then doing that. I don't think we are going for major rehabilitation or overlaying options. But these are options that are available. For that, we need to carry out a structural evaluation or metal testing of that, whichever inputs are required for a new design as per IRC 58 or as per low volume road design IRC SP, I think 62. Whatever inputs are required, you need to obtain them from the existing road. We can do an overlay design. If they're in a bad condition, we can always recycle them.
Thank you.
We've done that for national highways, not extensively for low volume roads.
No, I'm more concerned about the roads in smaller towns and particularly in streets where they put the concrete pavements because they don't follow the quality control. They're not conscious of quality control. I remember, you may be remembering H.S. Bhatia was there, Sardaji. I remember the quote he used to tell, concrete pavements are like a virgin. If you don't deal with them properly, they get spoiled. Thank you.
Yeah. Professor Kumar sir,
Yeah, good evening, sir.
Professor
So
Kumar,
Chairman sir and Sudhakar Reddy sir, very good evening. Very nice lecture. And I have a generic question, sir, regarding functional performance of cement concrete roads. Just if you look at practical, the stretch Hyderabad to Warangal, recently cement concrete road constructed. But my experience, a dozen times I traveled from Hyderabad to Warangal and Warangal to Hyderabad. Definitely, as per the index, that is more than 2000 mm, 2000 mm per kilometer. But the journey totally, totally discomfort, sir. But newly constructed. So in that case, what could be the solution to improvise that?
See, theoretically, concrete pavement, you should get a near planar surface. The joints are the only one which are going to give you that variation profile, which can induce vibrations. I don't know exactly what kind of a discomfort that you felt, whether it was a noise, whether it was were you feeling jerks?
Undulations, jerks.
Jerks. So
Jerks.
you would also feel those jerks at periodic interval, which is matching with the joint spacing. So even that small groove depth that you get is a sufficient variation in the profile which could actually produce those vibrations or jerks. I don't know whether the joint was cut too wide, because I'm sure you have traveled on other concrete pavements. So your experience is compared to other concrete pavements, I believe.
Yes, sir.
So I have a feeling the joint might have been cut a little too wide, maybe with a thicker blade than what should have been.
Even so many undulations are there, sir. Even the longitudinal profile of the cement concrete road is not good. So in that circumstances, is there any like alternative? See, to make up that defect, is there any alternatives available?
Long-term profile in the sense, even the surface, they could not finish.
Yes, surface is not proper, basically.
Okay. No, if you have to treat it, you have to grind that surface, and then unless it is very bad, you have to remove the slab, of course. But generally, those variations in the profile, if you can establish that, you can always grind it and remove that. But that is going to be too difficult, too expensive.
Even
did not construct it with a reasonable smooth finish. If you want to go on to repair that, it's going to be very difficult and then expensive.
Yeah. And at the same time, that PV Narasimha Expressway also earlier that constructed to airport in Hyderabad, totally too many undulations and very discomfort. And recently, I think they provided some bitumen layer over that. They just made some kind of smooth surface now.
Yeah, most of the concrete pavements, when they fail in this functional aspect, you resort to bitumen surface.
Yeah, only thing is, as T.S. Reddy sir said, no, concrete pavements should be dealt, in a very, very perfect manner. Otherwise, the riding quality will be very poor. That is my experience, sir. Yeah. So thank you, sir. Thank you.
Thank you, sir. Kumar, sir. Anybody else? Any question, please?
One question can I ask?
Okay, you can ask your
So, what type of overlay or a concrete pavement in city concrete roads do you recommend, Professor Sudarshan?
Yeah, I think cities, if you got good drainage facility available, you can remove water quickly. I won't mind bituminous overlays. But you got a drainage issue, water is going to be stagnating there. I would prefer a concrete overlay.
Thank you.
Are there any other questions?
Sorry to Reddy, I just want your comment on particularly Japanese expressways. I am told over the concrete pavement, which is under, the base one, and that they are trying to give bituminous surface course to make, riding smoother. Everyone is complaining, which everyone will feel that, if you're riding on concrete pavement, whatever precautions they take, they will not be able to achieve the perfect smoothness. So, what do you recommend? What are your comments?
These are actually standard options available even in USA also, both for structural overlay or mostly for functional, because either to reduce the noise and also for the roughness issue. So for both cases, the bituminous overlays are being used. They are also used as a structural overlay because you keep changing the policy. Okay, I'm now for concrete, now for asphalt. We have done that in India. So now most of our concrete pavements might be overlaid with asphalt layers. As to 1993, have got all options for all combinations. Of course, we can also do that in India. We don't have an ISA guidelines where I think we can provide asphalt overlay on a concrete pavement, unless we assume that I'm going to, the concrete road is badly damaged. I'm going to break it up into two pieces and then make it as a granular layer. So then it becomes a normal bituminous layer, bituminous pavement. That's one option. But on a good concrete pavement, if you want to put an asphalt layer also, that is also an option. design procedure is available. As to 1993, all options are available, even MEP design.
But don't you think we should have one, I mean, for our own conditions?
Yeah.
Thank you. Thank you very much.
Welcome, sir.
Thank you, sir. Thank you for wonderful answering of all the questions also. I think Dr. Raghavachary Rao is trying to come in between. Sir, are you there, sir? You want to ask any question? Okay, I think if no question is there, I request my Honorary Secretary to kindly propose vote of thanks. Dr. Venkata Sabbay garu.
Thank you, Chairman, sir. Respected Speaker, Dr. K. Sudhakar Reddy, Professor, Department of Civil Engineering, IIT Kharagpur, Engineer B. Brahma Reddy, FIE Chairman, IEI, Telangana State Center, Dr. T.S. Reddy, FIE, Scientist Retired, CRI, New Delhi, and Senior Consultant, LEA, Associates, South Asia Private Limited, and the convener of this event. Dr. S. Nagabhushan Rao, Dr. D. Hanumanthachari, Professor Ramana Nayak, Dr. G. Rameswar Rao, Pradeep Reddy, Professor Moinuddin, Professor Kumar, Professor Ramanujacharilu, Engineer Saripalli Suryanarayana, Engineer M. Srinivas, Dr. Sesham Anand, corporate members of Institution of Engineers, distinguished guests, family members of Dr. S. Raghavachary and students of Dr. S. Raghavachary, representatives of media, ladies and gentlemen. On behalf of the Telangana State Center of Institution of Engineers and on my own behalf, I convey our sincere and profound thanks to Dr. K. Sudhakar Reddy, Professor, Department of Civil Engineering, IIT Kharagpur, for delivering a wonderful lecture on the topic Design and Evaluation of Concrete Pavements. So my sincere thanks for you, sir. Once again, I am extending for you, sir. I would like to express my gratitude to past presidents of IEI, past chairman of IEI Telangana State Center, past honorary secretaries of IEI Telangana State Center, council members, committee members, corporate members, representatives of media, family members, and students of Dr. S. Raghavachary and others who made it convenient to attend this event. Thanks to one and all. Now I request all of you kindly join for national anthem. Ratnam, play national anthem. Ratnagar.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल हिमाचल यमुना गंगा जल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Jai Hind.
जय 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 हे जय हे
Jai Hind.
Jai.